Hello everyone. Welcome to the 10th lecture on the course Mathematical Modeling and Simulation. In this lecture we will talk about how to model epidemics. So before moving further, we will start with some basic definitions which you will hear all the time during this lecture. So the first one is an epidemic. Epidemic is a disease that affects a large number of population within a community, population or region. That means that if there is a disease that affects a large number of population at a short period of time, it is called as epidemic. Now what is a pandemic? An epidemic that spread over multiple countries or continents is called as a pandemic. Like for example, when COVID-19 when it was limited to Wuhan, it was called as an epidemic, and when it spread to the entire world, then it is called as pandemic. Now there is another word, that is endemic. So what is endemic? An endemic is a disease that remains in the population for decade or two. For example, malaria is endemic in parts of Africa. Also you will hear a word called as outbreak. So what is an outbreak? If the number of the infection is greater than the anticipated value, then it is called as an outbreak. So even a single case that is not expected can also be a reason for an outbreak. So if it is not quickly controlled, then what we can say, an outbreak can become a epidemic. So these are the words which you need to know. Now we will understand what do we mean by epidemiological model. So for this we need to understand what is epidemiology. So epidemiology is a field of science that studies epidemic diseases and the factors that influences its incidence, distribution and control. So if we use mathematical equations to write this epidemic disease, then it is called as epidemiological models. Many mathematicians use mathematical models to predict the epidemics, and obviously these mathematical models are only of use when the models they formulated are close to the reality. Otherwise they are of no use. And to keep the model simple, what we need to do, we need to make some assumptions and relaxations into consideration. So if we talk a little bit about the history of epidemiology, it has its root in the earlier 20th century. Sir Ronald Ross during 1857 to 1932 studied the spread of malaria, and he developed an important idea that we didn't have to eradicate all the mosquitoes to eliminate the disease. Then in 1927 Kermack and McKendrick developed a well recognized SIR model. What is this SIR model? Means susceptible, infected and recovered compartmental model in 1927 to study the outbreak of Black Death in London and plague in Mumbai. So they used these compartmental model to study the outbreak of these two diseases. This is a photograph of Sir Ronald Ross, who also got Nobel Prize in 1902, and this is Kermack and McKendrick. Now the question arises, why we need to develop such epidemiological model? So this will give you the following answer: how big outbreak will be, how will it develop over time, what are the key determinants of the epidemic. It can also guide the collection of data. We can also forecast the future direction of the spread of the epidemic, and we can also evaluate the potential impact of interventions. Now let's see the types of epidemiological models. So broadly speaking, there are two types, deterministic and stochastic. Now if you see by this figure, this deterministic is again broken down into discrete time and continuous time. So discrete time models can be formulated by the difference equation and continuous by differential equation. Similarly, the stochastic is again divided into discrete time, discrete space, continuous time, discrete space, continuous time, continuous space. So in this lecture we will restrict ourselves in this part, and we will talk about this continuous time model, that is SIR, SIS, SIRS and so on. I will tell you as the lecture proceeds that how we can develop all these kind of modeling. Now if you see about the differences of these two models, you know that the solutions of this deterministic model is always a function of time, or you can say space, and it is also dependent on the initial data. And if you talk about the stochastic model, the solution of the stochastic model is a probability distribution for each of the random variable. So we will we will study this stochastic model in the elaborative way in our coming lecture. Let's focus on this deterministic part for this lecture. So these are few differences between the deterministic and stochastic. Firstly, I will tell you the features of deterministic. In this deterministic model, individuals are categorized into compartments, and then the transition between the compartments are described by average transmission rates, and it aims to describe what happens on average in the population. It tells about the average happening in the inside the population, and the result imply the epidemic will take the same course. Like if you put the same parameters and same initial value, it will give the same result. And individuals are considered to be homogeneously mixing. Now what does this mean? This means that if you have a closed system, then every person over here has a equal probability of getting contact in with other person, right? It's not that the neighbor will have more probability. The homogeneous mixing means all the population inside this will have the equal probability of getting in contact with one another. Now if we talk about probabilistic, or you can say stochastic models, it incorporates the role of chance and variations in the parameter. It provides all range of possible outcomes, and it is relevant for small populations only. If we see both of this model, the main challenge is getting a good data for fitting the parameters. So if we get the good data, then we can estimate the parameter, and we could have a good future predictions about the epidemic or outbreaks. Now we will see how to formulate the epidemic models. So we will start with the basic SIR model, that is susceptible, infected and removed. So this model was developed by Kermark and McKendrick for influenza epidemic, and in this model they divided the population into three compartments. What are these three compartments? Susceptible, I have denoted it with S, infected denoted by I, and you can say removed denoted by R. I can call it as removed also. And we know that infected individual transmits the disease to susceptible individual, and we have taken that every infected individual transmits the disease to the susceptible individual with the mean transmission rate beta. And obviously I have told you that for formulating any model we have to make an assumptions. So this is the first assumption, that the population is considered to be large and fixed. That means that there is no birth, no death, no arrival, no departure. So this was first assumption. And second assumption is that latent period is 0. That means that as soon as the susceptible population comes into the contact with infected population, they start spreading the disease. Suppose that I am infected, right, and I come in contact with some healthy individual, you say that S, and then it will also become infected. Now it can immediately transmit the disease. So it is saying that latent period is 0. That means that it is not taking any time to be infectious. It immediately start spreading the infection. The third assumption is after recovery individuals are immune. When this infected population is came into this class, recovered somehow, then it will always be immune, that it cannot catch the same disease. So this is the third assumption. Now fourth, I have told you that we will consider the homogeneous mixing, that is everyone has a equal probability of coming in contact with one another, and we have considered the force of infection as this. This means that susceptible only comes into the contact with the fractions of infected. This is what? This is the fractions of infected individual per total population, right? So this transmission is called as frequency dependent transmission, and as I have told, only beta contact between the individuals and infective results in infection. It is not that everybody who is coming into the contact with the infected are getting the disease, only beta portion will get the disease. So with this assumptions, we have the following mathematical equation. Now you can see that as there was no birth and no death, it has no plus sign. So this is the susceptible is coming into the contact with the fractions of infected individual per total population, and when it is coming, this portion of beta is getting infected and it is going to class I. See how there is a negative sign and this is now with the positive sign. That means that the susceptible is leaving this class and going to the infected class, and this one gamma is the recovery rate. This one is a recovery rate, this beta is a transmission rate. So suppose that after some time this infected population is recovering and it is becoming immune. So this is rate is given by gamma, and this is removed from this class and it is adding to the this R class, that is the removed class, and you can see that this is completely removed and it is not going back to S. So this is called as SIR model. So this is a very simple SIR model, and I have already told you that beta is infection rate and gamma is a removal rate, or you can say as recovery rate. This is a very simple coupled differential equation. Even then we do not have a closed form of solutions for this system. If you do some numerical simulations for this system of differential equation with beta is equal to 0.7 and gamma is equal to 1, you will see this type of graph. Now if you just change a little bit of parameter, and if you set beta is equal to this and gamma is equal to this, you will see that there is a growth in the infection over there before it is dying out. So we will now introduce an important concept of reproduction number. So what is reproduction number? If you see the second equation, just see this second equation, and if I write this second equation over here, di by dt is equal to beta si by n minus gamma I. Now when this rate is greater than 0, let's see, then this equation implies this is greater than gamma by I, and if I write like this, beta s by n is greater than, you can say, 1. Now when this equation can hold true, you can easily see that this quantity s by n is less than 1, as n is a total population and s is a number of susceptibles, so it is always less than 1. So how this can be greater than 1? Only if beta by gamma is greater than 1. This gives us an important number that is called as reproduction number. Now you can see that this number is dimensionless because these two are rates whose unit is this. Beta has the same unit as the gamma. This gives you a dimensionless number. Now why this number is important? Because you can see that when this number is greater than 1, this means that rate of increase of infection is greater than 0. So this means that when my reproduction number will be greater than 1, infection will increase, and if it is less than 1, then my infection will go to 0. So this is the physical meaning of reproduction number. It describes the total number of secondary infections produced when one infected individual is introduced into the disease-free population. That means that suppose that you have a large number of population and you introduced one infected population. Now the numbers of the infection, it is spreading when this one is introduced into a susceptible population. I hope you understand that it is the total number of secondary infection produced when one single infected individual is introduced into the disease-free population. These blue one are disease-free and this red one is introduced, and how many secondary infection it is producing, it gives you the reproduction number. Now if it is greater than 1, then the disease can invade, and if it is less than 1, then disease dies out. So if you want to study about this reproduction number in more elaborative way, and also you want to find out the reproduction number for more complicated model, you can read this paper by Dykman and Hesterbeek. It's on the next generation matrix method for finding the basic reproduction number. Now we will see an example of susceptible, infectious, recovered, susceptible. What is additional in this? This word susceptible. Earlier we studied SIR model. Now it is SIRS. So what is the difference? Now the recovered class or the removed class can go into the susceptible class back. That means that they lost their immunity and they can get the infection once again. So here you can just see what is the additional part. Here loss of immunity term is over here, and then it is adding to the susceptible class. So again this do not have a closed form of solution, and just for showing some of the analytic result, I have already told that how can you find out the equilibria. You can just equate these equations equal to 0 0 and you will find two equilibrium points. These are given by E1 and E2, and this E1 is N00, and this is given in a compact form where R0 is given over here, C1 is given as this, and C2 is this. So you can put all these over here and you can get the second equilibrium point. Now we can find out the Jacobian matrix. This one is 2 cross 2 Jacobian matrix. How they have calculated? They have just substituted R with N minus S minus I. Now simply you can calculate the Jacobian matrix as I have told you in my previous lectures. You can find out the Jacobian matrix, and then what you have to do, you have to put E1 and E2 one by one. When you will put your first equilibrium point N00 over here, and then you will find out the eigenvalues of this matrix, you will see that you will find out the eigenvalues as these both. And when you will put E2 in this matrix and then again find out the eigenvalue, you will find out your eigenvalue to be this. Now why this is important? This is giving you the stability conditions. See, this one is negative and this one can be negative only when gamma is greater than beta. So if we want to make our disease free equilibrium, this is my disease free. See here, the disease component is 0. So we can call this as disease free equilibrium. So if we talk about the first stability condition, this is for disease free equilibrium, and you can see that this one and this one are the eigenvalues. So if gamma is greater than beta, then both eigenvalues are negative. Now if both eigenvalues are negative, that means that my E1 will be asymptotically stable, and if this one becomes asymptotically stable, that means that all the solution in the neighborhood of E1 will be attracted towards this equilibrium point E1. So we got a very important result that we should make this gamma greater than beta to make this E1 as locally asymptotically stable. Now let us see a numerical simulation for this. For figure number A, these parameters are set over here, and it is observed that for this R naught is coming out to be 0.95, which is less than 1. And you can see that disease is going to 0 in this case. You can see from red color one, the disease is going to 0. Now if you change the parameters, you can see that your reproduction number increases. It becomes greater than 1, and you can see that there is disease in the system. Here the red one is showing that infection is still there in the system. So you can see that how reproduction number can be helpful to see that whether the disease will be in the system or it will die out. Here is a vector plots. This first is showing that the equilibrium point will be a saddle point when R naught is less than 1, and it will become stable when R naught is greater than 1. This one is a graph for endemic equilibrium. Endemic equilibrium means the second equilibrium E2. That means that all the components was present in the system. So when R naught is greater than 1, then this endemic equilibrium becomes stable. You can see from the graph. Now let us develop the mathematical model for SARS epidemiology. So before developing any model, we must know about its biology. The SARS outbreak was the first outbreak in the 21st century, and if you see that it has a incubation period of about 2 to 7 days, with most common is 3 to 5 days, and the individuals recovers after 7 to 10 days, and it is serious with the people aging greater than 40 and having some other medical problems. And mode of the transmission is not very clear. It can be transmitted by person to person contact. Also it can be transmitted by contaminated objects, air, or by some other unknown ways. So this is the model, or you can say that this is a schematic diagram showing the compartments. So we have now S, this is for exposed, this is for infected, and this is for recovered. Now what is the additional? This class is an additional class, that is the exposed. So what is this exposed class? As you have seen that from this second biological phenomena, we see that the person become infectious after 2 to 7 days, right? So as soon as this infected population will come in contact with susceptible, it will get the disease, but it will not transmit others. So for taking care of that, it is first put into the exposed class. Means that a person is infected but it is not transmitting the disease. When it is in I class, it is infected and it is also transmitting the disease to other. I think that this one is clear, that what is the need of exposed class. For example, I transmitted the disease to somebody, but it will take 2 to 7 days to start becoming infectious. So after that period only he will come into the I class. So with these assumptions, we have the following differential equation, or the systems of differential equation. Here you can see what we have. The additional part is over here. Here I is coming in contact with S, and now instead of going to I, it is coming to class E, because first it will remain in the exposed class as it is not transmitting it to the others. This nu is 1 by incubation period, because this is given in rate. So this nu is 1 by incubation period. When this incubation period is over, this exposed class will go to the infected class, and obviously when this infection is recovered, it will go to the recovered class and it becomes immune. You can see that it doesn't go back to the susceptible class. So this type of modeling is called as SEIR models. So from all these things you can see that there are so many types of models, but you do not have to restrict yourself in SIR SER or SEIR. If the biology suggests you otherwise, you can develop your own compartments. So here is one last model which I want to show is that of SEIS. That means that here I have this extra component S and over here I have written with vital dynamics. Now what does this vital dynamics means? That now I have birth and death also incorporated in my system. Now I have not closed the system, but now it is allowed that we can have birth and death. So now you can see that my model will become like this, that here this is a birth factor, right? This is B is intrinsic growth rate, this one is growth rate, and this mu1 is natural death rate. So every other things I have already explained, but these were the two things which was additional for this model. So this is a type of SEIS modeling. So these are the other functions which you can consider as a transmission function. So this one we have used in showing our modeling. This is called as frequency dependent transmission. However, you have these different kinds of functions that you can use for modeling the transmission of disease. So this paper was given by McCallum, Barlow and Hone, and you can read this paper to have a better idea where these functions can be used. So now after looking this video, I want you to do some exercise. You know that recently coronavirus was hit and it is causing panic and death all over the world. 30th January 2020, WHO also designated it as a global health emergency. We also know that except vaccination, there is no specific treatment that can completely cure the disease. What we have to do, we need to develop some mathematical modeling and then simulate the spread of the coronavirus in any city and then discuss what are the measures that can be taken immediately and what are the implications this has for the policy making and management. So you can think in this direction. I will just show you one model that was given by these authors. You can see that they have taken a simple SEIR model, and this is the schematic diagram of their model. Here the parameters, what are the meaning of the parameters in the system they have taken, I have mentioned it over here, and for their system the reproduction number is coming out to be this. They have taken these parameter value. These parameter values are taken from the data, and when they simulated they got this type of graphs. So I hope after looking at this lecture you can come up with some new models and can show some new results. So I will end my lecture over here. Thank you.